Hi everyone, in this lecture we are going to start new topics related to equilibrium of a particle. In the module 2 we have learned how to perform summations of force vectors in two-dimensional and three-dimensional systems. And if you could recall what we have learned earlier in this course, there are three important keywords that define this course. One is the equilibrium, right? Second is the forces, equilibrium of forces, and third is the body, which is equilibrium of forces that are acting on the body. Okay, so we have learned how to deal with the forces in module 2, and in here in module 3 we will talk particularly how to impose an equilibrium conditions on a specific body. In here is the particle. Okay, so before we start it, let's say this is our particle. In here the equilibrium conditions that we are talking related to particle is to restrict the motion of the particle in translational manner. Okay, so for example, if this particle is located in two-dimensional space, which is in this plane right here, the particle can either move upward vertically, right, or horizontally, right, which is these two motions are independent to each other, and it can use to define any motions in the two-dimensional plane. Okay, in three-dimensional space, this particle will have an additional translational motion, which is in these directions, right, in this direction. Okay, so there are three independent translational motion for a particle located in three-dimensional space, which is vertically, horizontally in this direction, right, and horizontally in this direction, which is coming out from the plane that from the two-dimensional plane that we talked earlier. Okay, with those three translational motion, we can define all of the motions of the particle in three-dimensional space. Okay, so basically the equilibrium equation that we are going to set up in here is to restrict the motion of the particle such that any forces that is acting on the particle will not cause this particle to move. Okay, all right, or even if move, it has to move with a constant velocity. Why? Because constant velocity will not exert any accelerations, as you have learned in physics, and since it doesn't exert any acceleration, it will not exert any additional forces to the system. Okay, all right, so let's get started by setting this up for a two-dimensional system. Okay, so for two-dimensional systems, let's consider that we have the axis x and y in here. Let's say we have the x and y axis. Okay, and then let's say that we have the particle right there. Okay, and we have forces that are acting on the particle right here. Okay, and let's call that forces F1, F2, F3, and F4, right? And as we discussed earlier, that in two-dimensional system there are two translational motion, which is along the x-axis and along the y-axis, right? And such that the equilibrium that we set up in here has to restrict that motions in the x and the y directions. And we have learned in module 2 that Fr, which is the resultant of all of the forces acting on the particle, is equal to Frxi plus Fryj. Okay, and in here Frx is sum of the component of the forces in the x directions, and Fry is sum of the components of the forces in the y direction. Okay, So to satisfy equilibrium conditions, we have to set up this force equal to 0. Okay, when it's equal to 0, then we can make sure that this particle will not move, will stay in this position, or even if it's move, it will move in a constant velocity. Okay, and in many problems that we discuss in here, there are many cases where the particle are attached to some component or some structures, and the most common components that we will encounter when we solve problems is one, spring, right? Second is cable, right? And sometimes it can be even be just rest on a surface, right? Rest on a smooth surface such that there's no friction involved in here. Okay, so I believe you guys have encountered similar things when you learn physics. In here we will just try to review how to deal with these components. So remember that for the springs, if the spring has its initial length of L0 right here, okay, if the spring has an initial length of L0, and then when we apply force F, right, the spring will be elongated by a displacement of S, right, such that its total length right now becomes L. We know that S in here is L minus L0, right? And if we know the stiffness of the spring, right, we can calculate F as K times S. Okay, and then for the cable, okay, and in here we assume that the pulley in here is frictionless. So when we solve problems, in most of the case we assume that the pulley is frictionless unless it's stated otherwise. Okay, so in this case, if we have a continuous cable attached running through the pulley in here, okay, running through the pulley, if we know that the tension of the cable in here are going to be the same. Okay, so if the forces in here is T, then the forces in here is also T, right? Oh, I think it's better to call this as a continuous cable running on a frictionless pulley. Okay, such that it's in line with what we already discussed. Okay, so I'm going to continue with the last components in here, which is if for some problems the particle will rest on a surface, and in here particle is rest on a smooth surface. And for example, if this particle, we have a particle and it rests on a smooth surface right here, right, and if we remove the surface, we will see that there is a contact force that is perpendicular to the surface, and let's call that this contact force as N, right? And of course, if there's another forces acting on the particle, we have to draw that as well. For example, if I have force T in here, and usually there's also a weight that we have to consider. Okay, so depends on the problem. Sometimes we need to consider the weight, sometimes we don't need to consider the weight. If the weight is given in the problems, then definitely we need to consider that. Okay, I think that's it for this lecture, and thank you for listening.